thousand little ways he's changed. Yes, indeed. You know he's moving up metal if he's hanging tight. Check out the speed. Okay, howdy, Ags. It is time for our next installment of Exercise Biomechanics. And today the focus is going to be our first installment of Applied Kinematics. Applied Kinematics. So what is Applied Kinematics? Well, it's basically using observational data to try to make to try to analyze what goes on with mechanical systems in the body. So while we're moving around, while we're playing tennis or golf or running or maybe playing volleyball, etc. So kinematics is a descriptive analysis, but it's hard for us to actually just talk about descriptive analysis when we want to get at really what are the causal reasons that we might, for example, alter a baseball or a softball swing to try to hit the ball a little harder and to try to hit it farther. We might be looking at, for example, maybe a golfer who wants to be able to play a little bit better and maybe hit the ball a little bit faster. So there's a couple of golfers that are in the PGA Tour. One of the things you may have noticed if you follow golf at all is that you're seeing people doing a lot more workouts and becoming a lot more athletic to compete because they want to hit the ball farther and straighter. So this happened initially with Tiger Woods, but over the last really 20 to about 23 years, what we've seen is an increased interest in fitness in golfers. It's kind of like the last sport to try to catch up with the science of exercise. So Brian DeChambeau, for example, gained about 40 pounds in the last 6 months to try to increase his power. We're going to talk about power today and how that relates to locomotion. Power is the ability to do work over a period of time. In other words, to do work quickly. And because work can be seen as a product of force times distance, power, if we do a little derivation, is really a combination of force and velocity, So we can focus on, when we using the specificity of training, if we think about trying to train for sports that have a significant amount of power. We sometimes see this in golf and especially like tennis, baseball, basketball. Shot put's a classic example of a power sport. If we think about, for example, Olympic lifts, a great deal of power goes into Olympic lifts. Ironically, there's actually very little power that goes, believe it or not, into the so-called power lifts, the bench press and the deadlift. Because the movements for a maximal lift are relatively slow, there's actually not a lot of power, because if you multiply a large force times a small velocity, you get a relatively small number. Both numbers, or both variables, have to be relatively high. So I'm cleaning my glasses. That's why I had this little towel out. There we go. That's nice and clean. That's good. So we're going to start looking at variables like distance and arc, and that's going to lead us to movement, and that means speed or velocity. So the advantage, for example, in the laboratory, we're going to capture lots of little clips where we can analyze a sequence of images. When we're analyzing movement, you need multiple images to look at a change in position, change in location over time, and that's what helps us to calculate things like velocity, acceleration, etc. It's really it's not an abstract. It's really based on the ability to make measurements, and the ability to do that is by looking at a series of pictures. Now, we're lucky today is we have computers and computer programs, including ImageJ, that we're going to be using for frame-by-frame analysis. And also we use Dartfish, which will help us to calculate velocities and accelerations over multiple frames. So it's about collecting moving pictures. When you're taking video, for example, with a video camera, there's some factors you have to remember. One of the critical ones is the film speed, and that means how many frames or pictures you take per second. That's going to help us to calculate things like velocity and acceleration. If you do some measurements, you're going to learn about f-stop, and that's how wide the iris is open. You're going to learn about shutter speed, and that basically is how fast the shutter can open and shut. And for example, the shutter speed on our Sony and our slow-mo or high-speed cameras, they can go to about 1/10,000th of a second. So they can pretty much capture just about any image, anything that's moving out there, whether it's a baseball or softball or tennis ball or a golf ball. And it captures really sharp images if you keep that shutter speed low. So, okay. Well, because it's all about measurement, the purpose of actually going through applied kinematics is so that we can make some measurements, collect some data, participate in some scientific inquiry where we'll actually do some experiments. You'll get a chance to design your own experiments during the course of the class. So let's get started. So we talked about position and time, basic stuff last time. So now we're going to actually start using it. So when we look at a variable like distance or displacement, we're going to look at the angular analog as well. So for distance and displacement, we have arc or angle. And then when we focus on linear velocity, then we'll talk about angular velocity. So let's get started. Distance or displacement is basically movement that occurs over some period of time. We're going to measure that in terms of the same units we use for position. So distance is a length that's traveled. It can be rectilinear, a straight line, can be curvilinear. The units are in the English system are feet, and in the metric system are meters. These are standard for whole body biomechanics, and we could be looking at something moving in two-dimensional space, maybe in a straight line. We could be looking at, let's say someone is putting a football, and we're looking at that movement over time. It's going to follow a parabola. Gravity is going to act downward the entire time. The X component, we're going to ignore fluid drag for the moment. We'll say is not going to be changing. Once that ball or once that football goes up in the air, its downward speed or upward speed initially, and then downward speed is going to be constantly changing at 9.81 meters per second squared or 32 feet per second squared. But that X component, we'll say, is not changing at all. Okay, so when we're calculating linear, rectilinear distance, straight line distance, we can use a number line for one dimension by simply looking at the change in the different positions. For 2 dimensions, we can use the Pythagorean theorem and calculate it as the change in the X variable. The change in the Y variable will square delta X and delta Y. We'll take the square root, and that's going to give us the hypotenuse, which will be the distance from the first coordinate to the second coordinate. In 3 dimensions, one of the ways we can calculate this is actually expand the Pythagorean theorem from 2 dimensions to 3 dimensions and add delta Z squared. So that distance, again, is the square root of the sum of the squares of each side, and each side is basically the change in the X variable and the change in the Y variable. Sometimes, like when we're running around a track, we're going to follow a curvilinear path. The first part will be curved. It's basically half a circle, if you will. And then the last part of the 200-meter race looks something like this. So in these 200-meter races, you actually have to accelerate as you're increasing velocity and turning around that curve. By acceleration, we mean we're increasing our velocity, and then we're trying to maintain it during that stretch during the last 100 meters or so. So it's a challenging race. That's actually the curvilinear or linear distance. If I move in a straight line, that's actually displacement. Displacement is the difference between where you started and where you ended up. So let's pretend you run 100, well, let's make it a 400-meter race. If you run a 400-meter race, you run all the way around the track and finish where you started. So anybody who's run 400 or 800 meters knows how difficult those two races are. They really burn, because after about 150 meters or so, glycolysis really starts to turn on. And because humans take about 2 minutes, 2 to 3 minutes to get oxygen consumption up to a plateau, that means you're generating lots of lactic acid. That's at the tail end of glycolysis. And you can't convert it back to pyruvate, where it can be used by mitochondria, because mitochondria are a little bit slow. In humans, takes about 2 to 3 minutes. In a dog or a thoroughbred horse, it's about 70 seconds or so. And horses actually have an additional benefit. They blood dope when they start to run. So you might say, how do they do that? They inject themselves or what? No, they actually, their spleen contracts. And when their spleen contracts, it releases a couple 100 mLs of blood. And that blood actually goes up to the lungs, get oxygenated. And so they blood dope. Every horse gets the blood dope when they start to run. And that's one of the reasons why a thoroughbred can clear a mile in about 2 minutes. In fact, I think that's the record in the Kentucky Derby, which is almost exactly a mile. And it was set by Secretariat way back in the day, 1973. So when we're running the 200-meter race, the only chance I have against these folks, and I probably don't even have that anymore, would be the displacement. Just to run straight across the infield, straight to the finish line. I might have a chance, probably not. I'll probably lose today. But that would be my only chance, is to go for the displacement as opposed to the distance. So we're going to do a little distance calculation by looking at a set of X and Y coordinates, or two sets of X and Y coordinates. The first set corresponds to the first position, and the second one corresponds to the second position. So I'm going to pretend that I have a super high-speed digital video camera. I'm going to take a video and look at this baseball over consecutive frames. So for the first position, we've got an X component of 10 centimeters and a Y component of 15 centimeters. And that ball is going to move from 10 and 15 on the X and Y direction to positive 30 and positive 40 in the Y direction. So we go from 10, 15 to 30 centimeters in the X direction, 40 centimeters in the Y direction. If we take the difference between the X components and the Y components, we can then calculate delta X and delta Y. Once we're able to do that, then we can actually calculate the distance traveled. We're going to assume that the ball's hit so hard, and we're doing high-speed video cameras, that we're catching it at a part of the trajectory where we can assume that the ball is more or less going in a straight line. It's not quite true. It's actually curving as gravity is taking effect. But when we're looking at a high-speed camera that might capture 500 frames per second, I think we can probably get away with it for maybe 2 or 3 consecutive frames. So let's take a look at our problem. We're going to set it up like this. Here's our y-axis. Here's our x-axis. And we're going to start at plus 10 in the x direction, plus 15 centimeters in the y direction, move to plus 30 and plus 40. So that means that delta x is basically 30 minus 10, or the second x component minus the first x component, or 20 centimeters. Delta y would be y2, that's 40 centimeters, minus y1, that's 15 centimeters. That gives us 25. So these are the two sides of that right triangle. The reason we can assume that this is a right triangle is because our x and y axes are perpendicular with each other. This is also true for the x and z axis and the y and z axis. So with that in mind, our right triangle will allow us to be able to calculate the distance. So if delta x is 20 centimeters, so we're moving from 10 units to 30 units, 30 centimeters in the x direction, from 15 centimeters to 40 centimeters in the y direction. That means this distance, the hypotenuse, will be the square root of the sum of the squares of the two sides adjacent to the 90-degree angle. So that's 20 squared plus 25 squared, that's 400 plus 625. That's equal to 1,025. I take the square root, and that's 32.02 centimeters. Let's say I had a film speed of, I'm going to make the math easy on me, 100 frames per second. If I knew that, and these were consecutive frames, there would be 1/100th of a second between each frame, each picture. And that means if I want to calculate the velocity, that would be distance divided by time, 32.02 centimeters divided by 1/100th of a second. So I could, let's see, figure that out. This 100, well, that's going to be easy. I made it easy on myself. So that would be 32 meters per second for the linear velocity, 32 meters per second. So that's about 60, 70 miles an hour. Okay, so arc or displacement. We got to update. Let's see. Put this in. There we go. When we're calculating an arc is a change in angular position. There we go. So we're going to take the difference between two angular positions. It could be, let's say someone is pitching fast pitch softball, and let's say the axis of rotation in the middle of the circle is the shoulder. So as they're moving their arm and that softball, let's say it goes from 132 degrees to 260. How did I get that? Well, I have to start at the origin. So if I rotate counterclockwise, theta 1 is about 132 degrees. That looks reasonable. And theta 2 is not quite 3/4 of a circle, which would be 270 degrees. So this is 260. So now I'm going to take the difference between the two. So that'll be 260 minus 132. And that indeed is going to be 128. Let's see. Oh, we've got a font problem. I've gone back and forth between computers, and I've been updating notes, etc. So occasionally we run into a font or another issue that I haven't quite picked up. So my apologies. This is live teaching, live learning. It's like live TV. Anything can happen, right? Okay. So then quickly, we'll take the difference between those two positions. Right now, I'm not concerned about the direction of the movement. In some cases, I will be, especially when I'm trying to calculate a joint angle. It will be really important if I have a body segment that's beneath the origin and I rotate clockwise, I have to give that a negative number. Right now, I'm just trying to take the difference between these two angular positions. So that's 260 degrees minus 132, or 128 degrees. So sometimes when we calculate a joint angle, this is a classic example here. Here we see Alan Johnson. This is an Olympic gold medal winner. And boy, he's really making an effort. You can tell the tongue is out. Check this out. Look at the leg, almost perfectly horizontal. But remember, when someone is clearing the hurdles, we want to try to maintain that center of gravity. If we move it up every time we go over the hurdles, that's extra force, extra energy that we need to propel ourselves upwards. That's going to slow our forward movement. We're definitely going to lose the race. So that means the torso goes down. Lead leg goes up, torso has to go down to maintain that center of gravity. So we can overlay, for example, the upper leg and the torso like a stick figure and calculate the difference between them. Because as we look at this hip joint angle, the origin is going to be in between the torso and the upper leg. That means we're going to rotate counterclockwise to get the position of the torso. That's plus 26 degrees. Here's my calculation here. The hip angle is equal to the torso angle minus the upper leg angle. So I've got 26 degrees. The upper leg's only about 8 degrees below the origin. So I rotate clockwise. Now I'm going to get the difference between the two, which is 26 minus negative 8 degrees. When you subtract a negative number, that's the same as adding a positive number. So, excuse me, 26 degrees plus 8 is equal to 34 degrees. So that is the hip joint angle. That's really tough. One of the things you wouldn't be surprised to know and learn, if you don't know already, is that hurdlers have to do lots of flexibility exercises, like no kidding, because you can't generate, I can't generate this angle anymore. Maybe when I was about 25 or 30 or 35, maybe with a lot of stretching, I could have done it. So it's just another stimulus to work out and do flexibility exercises, etc. Starting to do some for my shoulder. I used to wrestle, and now that right shoulder is starting to give me some business. The AC joint's a little sore, may have a little bit of arthritis in here, and then I think I've got also rotator cuff issue. Man, everything catches up with you eventually. So we're going to do another problem. This time we're going to take an arc or an angle and make something called an arc length. An arc length, remember, is the curvilinear distance on the outside of a circle. Because it's linear, the units are going to end up being linear units. So for an arc, for example, those types of units would be degrees or radians. Technically, radians would be the standard units. We calculate the arc length. That's the product or the combination of the arc expressed in radians and the radius. Radius is basically the distance from the middle of the circular axis of rotation to the outside. Now, the good news is that our body segments can be often thought of as like a radius around which rotation occurs. Like for the forearm, so we can have a radius here as well, and you can have a radius for the arm if you're doing fast-pitch softball, or if you're kicking a soccer ball either around the knee or the hip joint. So this makes the calculations a little bit easier and helps us to understand certain concepts. And that is, for example, if someone's going to throw an object, could be a baseball, could be a javelin, or even serve. The longer the radius is, the faster the arc, or the faster the either hand or the racket head or the club head is going to move. In fact, you can even think about a tennis racket as being an extension of someone's arm. And that adds to that radius. The reason that that's important is that if the radius increases, the longer the radius, the longer the arc length for a given arc or angle that's covered. Okay, so as we go through this, we'll emphasize that again, hope to make it clear. So Susan's performing elbow flexion arm curl exercises with a 5-kilogram dumbbell. The distance from the elbow to her palm is 35 centimeters. That's going to be the radius of the circle. The elbow right here is the axis of rotation, flexes through a 105-degree range of motion. So I'm just going to follow the forearm around the elbow. I'm going to assume the humerus stays in the same place. So I hate to say sorry, I'm taking a little bit of shortcut. Won't do it too often though. Let's find the arc length traced by the dumbbell. So with a radius of 35 centimeters, whatever the units are for the radius, those are going to be the units we use for the arc length. Arc length is a length. It's not an arc, it's not an angle, it's actually a curvilinear length, but it's still a length, just like running around a track. You run 400 meters, you finish up where you started. You can't tell anybody who's run 400 meters because that last turn really gets you that they haven't gone anywhere. They have. They've followed that curvilinear trek around the track. So with a radius of 35 centimeters and an arc or an angle of 105 degrees, find the arc length. So one of the things we need to keep in mind is we'll have to convert those degrees into radians to calculate the arc length. So we have 105 degrees. And this is an old trick I learned in chemistry way back in the day. When you're converting units, and when I'm going through a number of steps, I usually try to divide them into discrete steps. Show all your work. The more work you show, in your problem sets, either on a quiz or on an exam, the more points you're going to get. I like to set up ratios. So for example, I know there's 1 radian and 57.3 degrees. This is one of the few conversions you'll have to remember. So if we multiply 105 times 1, divide by 57.3 degrees, the degrees cancel out. We're left with radians. Good, very good. So we got 35 centimeters times 1.83 radians. That's 64.05 centimeters. So that's the arc length we've actually gone through. Okay, so now that we've gone through distance and arc, we want to look at what happens with a change in motion. So multiple pictures over time. So now we're going to talk about linear and angular velocity and start looking at some applications. A change in linear distance divided by time is linear velocity. And there are a number of ways, of course, we can calculate distance. We can calculate like arc length, if it's curvilinear. We can calculate 2 or 3 dimensions or a single dimension. If it's 2 or 3 dimensions, we can use the Pythagorean theorem. The units are not surprisingly units of distance divided by time. Standard units for time, remember, are seconds. So it's feet per second and meters per second in the SAE and the metric system. So one of the things to keep in mind, especially now that we're doing a lot of digital video, is that we can look at fairly short periods of time and get closer to instantaneous velocity. We'd have to do some differentiation to get it just right. But the point is, in other words, look at the slope at any given time. But the point is that we can take an average over a period of time. The longer the time is, the rougher the average is, because it's not going to tell you what happens in between. So for example, here's some sprinters taking off from the blocks. At the very beginning, they're going very slow, but they're going to reach a peak speed of about 25 to 27.5 miles an hour. That's about a little over 12 meters per second, pretty fast. But over the course of the entire race, the average is 100 meters divided by 10 seconds is a pretty good time. It's not world record time, but pretty good. That's roughly 10 meters per second. But at the beginning of the race, they're going to be running slower. In the middle of the race, they're running a lot faster. And even at the end of the race, they're still running pretty close to that peak speed. So here's this amazing athlete, Usain Bolt, who's very tall for a sprinter, 6'5", 6'6". And what made him unusual, most of the time people who are really tall can't get a high stride rate, but he could. And that, I think, is actually the difference. It's not that his stride length was a little bit longer, it was, but the fact that at that size and stride length, that his stride rate was so high. Because we know from data that I'm going to show you that the key variable we increase as we sprinting and going faster and faster is that stride rate to increase running velocity. So I did a little problem in one of his gold medal and world record races. I think he set 3 world records. I lost track of the number of gold medals he won. It's about 8. So Usain Bolt reaches the 50-meter mark in the 100-meter dash at 5.21 seconds. And at the 80-meter mark, he's at 7.65 seconds. The reason I picked 50 to 80 meters is that he reaches his peak speed about 50 meters out. That's a little late, 50 to 55 meters out. Most of the time, people reach their peak speed at 30, 40 meters and maintain it till about 70 meters. But Usain Bolt reaches it about 50 meters and then maintains it to probably 80, 85, 90 meters out. That means he doesn't slow down at the end of the race. So that's why you see Usain Bolt is really close to everybody else during the first 40 meters. But as they reach their peak speed, he keeps increasing. And then he doesn't slow down as much over the last 30 meters. And that's the difference. That's why he's getting that separation. It's not that he's accelerating past them. It's just he's reached a higher peak speed that gives him some separation. And then everybody else slows down more at the end of the race. So that's where that comes from. So we're going to do this problem. So we're going to look at the change in position divided by the change in time. So hopefully it'll be pretty straightforward. 80 meters minus 50 meters is 30 meters. He ran that in 2.44 seconds. So when you're in the middle of the race, like for example, when people time the 40 for NFL candidates in the combine, you know, 4.42, 4.3 is just wow. Everybody's freaking out. You know, even 4.4s is pretty good, especially if you're something like a quarterback. But that's over 4 seconds for 40 yards. So the reason that this is a lot shorter is they're already close to their peak speed. And so they're just maintaining that speed. That really, and this is where Usain Bolt is getting that separation from most people. So we got 30 meters divided by 2.44 seconds. That's 12.30 meters per second. This is pretty much his top speed, the top speed we've ever been able to calculate in a human. That's 27.5 miles an hour. Pretty amazing. If you're on a really good bicycle and you're in reasonable shape, if you can hit 27.5 miles an hour, you're doing pretty good. So that gives you an idea. Most people are in good shape on a bicycle. If you're on like a Tour de France, a professional grade cyclist, and you have a VO2 max of 80 mLs per kg per minute, or really high lactate threshold, yeah, you can go faster than that. But on a regular, typical bicycle that you might rent or you might own, that's probably about as fast as you're going to go. So it's amazing. However, you know, compared with the animal kingdom, elephant can run just about the same speed. Oh, cat can beat you. That's kind of my cat's so lazy and obviously doesn't train. It's kind of depressing to think, especially now, it will just cream me in a sprint. Greyhound can go about 45 miles an hour. A lion, not for very long, for a few hundred yards, about 55 miles an hour. And you guys know the fastest animal in the world is the cheetah. And the cheetah can only do this for 2, maybe 300 meters. And then it's got to rest for 30 minutes, 5 hours, quite a while. So it can't make any mistakes when it's going for prey. So there aren't a lot of cheetahs around because people have kind of gotten into the habitat, unfortunately, too much. The cheetahs don't have a lot of room for air, and there's a mating issue that I don't quite understand. But nonetheless, that's why they're rare. We got to protect these animals. So the point is, we're really just kind of meh, you know, as far as sprinters. And this is the best of us. So the average person can't run anywhere close to this fast. So we're upright. We've got the neck of the femur is at an angle where we can run. So what can we do? Well, I mean, there's got to be a reason we're upright besides using tools. There has to be another advantage, is there? Well, it turns out that even though most people don't want to go out and be endurance runners per se, humans are pretty good endurance runners on average. So we have a number of advantages. We sweat. We can redistribute our blood flow. We have light hair for the most part all over our body. That's great with heat dissipation. We can run at a pace that forces most animals to either have to trot or gallop, in which case they have to use a lot more energy. They don't dissipate heat as well for the most part as humans, even though in a summer day, I don't really want to go necessarily outside and even mow the lawn. I do some running, but I wait until like the evening this time of year. And sometimes we'll even hit the treadmill, even though I'm not a treadmill fan. But our ancestors are pretty good at running. We were born to run. That gluteus maximus really helps. So sprinters are just kind of freaks, really, in terms of human evolution. They're there. It's pretty cool to have. But it's the endurance aspect in people, the ability to dissipate heat and in groups to catch prey. That's actually why we're here as omnivores. Sometimes we need some protein, and we don't always have beans and rice and other whole protein sources around. So that's why people occasionally will eat meat. You don't have to eat meat every day. Our ancestors actually didn't for the most part. And when they did, they either engorged like at a festival, party, etc. After game had been caught. But during the rest of the year, they would either salt or dry the meat and eat a little bit at a time. And also people need iron. So that's another reason. Okay, so we're going to do another problem using the velocity equation, but I'm going to flip the velocity equation and actually calculate time here. So this is this normally would be baseball season. The baseball players and the owners are trying to work out when they're going to get started. We know the NFL is going to start sometime in the fall. Golf is around, even though there's nobody on site for the most part watching the golf. And I think the NBA is going to start in Disney World, right, in July. So if you're watching this and it is July, well, you're closer. You're closer to seeing NBA basketball. So they'll have a shortened rest of the season, and then the playoffs. The playoffs are the fun part anyway, so I'm glad they're getting to it. So maybe in some one way, it's not such a bad thing. Okay, so let's say a fly ball is hit to Yasiel Puig of the Los Angeles Dodgers in left field near the warning track, but not at the warning track. Jose Altuve of the Houston Astros is tagging up at third base. When Yasiel Puig catches the ball, he's 280 feet from home plate. Jose Altuve takes off for home at an average speed or velocity of 25 feet per second. Yasiel Puig throws the ball. I'm going to give him, it's probably a long movement time, 0.75 seconds of movement time. And once he releases the ball, it moves at 110 feet per second. Does the ball or Josh arrive first? So this is an Abner Doubleday problem. If Abner Doubleday really invented baseball, there's some debate about that. But nonetheless, the way baseball is designed and the diamond's designed is the rules ensure a number of close plays to make it more exciting, and so that it emphasizes strategy and speed and athletic ability. So let's say in left field, Yasiel Puig is 280 feet away. The velocity of the ball is going to be 110 feet per second. We've got some movement time of 70.75 seconds, sorry, 3/4 of a second. Jose Altuve is 90 feet from home plate, 90 feet between bases in the major leagues, and is going to run at a velocity of 25 feet per second. Now we try to find is the shortest time. So velocity is equal to distance divided by time. We're going to do a little simple algebra. Isolate time, we multiply by both sides and divide both sides by velocity. This is why the units are so important, because the units will tell you if you've made a mistake or not. So we'll start with velocities, distance divided by time. We'll do a little bit of quick algebra. Now we've got time is equal to distance divided by velocity. So that's feet divided by feet per second. The feet cancel out. We're left with seconds. So for Yasiel Puig, the time will be 2.55 seconds plus 0.75 seconds. So 3.3 seconds from the time Yasiel Puig caught the ball when the runner can take off from third base to home plate. It's the after a fly rule. And then throw it home at 25 feet per second. So the ball, therefore, gets there in 3.3 seconds. Jose Altuve gets there in 3.6 seconds. So the ball actually arrives first about, 0.3 of a second. Now, this is actually significant because for the catcher, let's see, for the catcher can catch the ball and make a sweeping tag in about 0.3 seconds. It takes roughly close to 1/3 of a second to make a tag. So that means that the play is going to be very close at home. There are some relatively new rules in the last decade or so that limit sliding cleats first right into the catcher. So we're trying to make the that play not only close but safe. That's always a challenge. So the ball does arrive first, but just barely. Okay, instantaneous velocity. To get anywhere close to that, we need high-speed digital video cameras. That's really what it's all about. Going to emphasize that right now. So the closer we get to instantaneous velocity by having a high film speed and using digital video today to be able to capture that, the better off we're going to be. Okay, if linear velocity is the change in position over time, linear position over time, angular velocity is the change in angular position or arc divided by time. So we're going to use omega as our symbol for angular velocity. It's the change in theta, change in arc or angular position divided by time. Remember, with angular velocity and angular acceleration, technically there's no difference between the English and metric system. We're going to use radians per second regardless of what system we're going to use when we're looking at linear terms. So radians per second are the standard units. They're the standard units. Okay, we're going to do a problem with Shane Lechler, who recently retired from the Houston Texans. I think in 2 or 3 years, we're going to see him nominated and get in on first ballot to the NFL Hall of Fame. He'll be the second punter to be in the Hall of Fame. Ray Guy, who also played for Oakland, it was the first. And that was way, way back like in the 70s and early 80s. Shane Lechler played for Oakland, and also he played for the Houston Texans. When he played for Oakland, he got a lot of punts in because Oakland was pretty bad for a long, long time. They won the Super Bowl like 15, 20 years ago, but haven't been too good since then. So during the final swing of his lead leg, 1.25 seconds into the swing, he's going to make contact with the football, or just before he makes contact with the football, sorry. His upper leg's at an absolute angular position of 110 degrees. That's from the origin. The lower leg is at 220 degrees. I put degrees in there and it didn't. Okay. 2 frames later, his upper leg's at a position of 127 and the lower leg's at 262. If the film speed is 60 frames per second, find the angular velocity of the knee joint. So in this problem, I'm going to show you, because we're using digital video cameras, how we can use film speed and knowing the number of frames or pictures that have elapsed to actually calculate delta t, or the amount of time that's elapsed. So we're going to go from frame 1 to frame 3. Keep that in mind. The difference was going to be 3 minus 1 or 2 frames. So there are 3 pictures. We're going to look at the first and the third one in order to calculate the angular velocity of knee extension. So we're going to be able to calculate his knee joint by first looking at the upper leg and lower leg angular positions. We'll take the difference between the two. For the third frame, we're going to take the difference between the lower leg position and the upper leg position. So that's 220 minus 110 for the knee joint angle in frame 1. For frame 3, the knee joint angle is 262 minus 127. One of the things that this is telling us is that that upper leg, notice how it's moving up, it's flexing for sure. And then that knee is extending. So we're going to see, that change in the upper leg position and then a big change in the lower leg position. So this delta is probably going to be a bit higher than this. Nonetheless, when we calculate a knee joint velocity, it's important that we calculate the knee joint angle for each of these 2 frames. So calculate the difference between the lower leg and the upper leg for both frame 1 and frame 3. And a film speed of 60 frames per second. There we go. Okay, film speed of 60 frames per second. So theta 1 is 110 degrees for the upper leg. For the lower leg, it's 220. Remember, we're always measuring the knee joint angle on the inside of the joint, measured on the inside, not the outside. So moving away from the anatomical position would be flexion. Moving back to the anatomical position will be extension. That's what we're seeing here. But the leg is moving back so that the knee is getting closer to that 180 degree angular position we would see normally at the anatomical position. So the knee joint angle in frame 1 is 220 minus 110 degrees. That's 110 degrees. And for frame 3, it's 262 for the lower leg minus 127 degrees of rotation counterclockwise. So that's where those numbers come from. 262 is a little under 3/4 of a circle. 127 is kind of about halfway in between a 90-degree angle and then a 180-degree angle. So 262 minus 127, that's 135. These are the knee joint angles. So let's look at the knee joints. Does that look reasonable? That's a little over 1/4 of a circle. And this is kind of halfway in between a 1/4 of a circle and half a circle. So it looks good to me. One of the things to remember is their knees should be a little flex when they hit the football. So they want to be able to strike their foot. So they're accelerating and increasing their velocity through the football, and they don't reach full extension until after the football is well off the foot. So let's finish this problem. Omega then is going to be the change in the knee joint position from frame 3 to frame 1. So that's 135 minus 110 degrees. Then we're going to take the change in time. And because we're using digital video, I'll show you how we can standardize and calculate that. So we're first going to start with a formula. Yeah, you guys are going to have to re-remember formulas. But formulas are rules. They just tell you what to do. So in this case, delta t is the reciprocal of the film speed. So you divide the film speed by 1, or into 1, and the units for film speed will be like frames per second. So you can have a film speed. Normally digital video is 30 or 60 frames per second, depending upon which software you use. High-speed digital video can be 100, 200, 300, 500 frames per second or more. It looks really good on slow-mo. You see this sometimes in baseball. There's a Fox cam for baseball. There's also, I think, maybe a Minolta or something cam for golf. But nonetheless, when you see these objects moving in slow motion, it looks really cool, especially when you're looking at a curveball curve in baseball. So because we've moved from frame 1 to frame 3, this part of the equation, delta, that's always the change in frames. So we're going from frame 1 to frame 3. If this were consecutive frames, meaning moving from frame 1 to frame 2, or frame 3 to frame 4, or frame 5 to frame 6, the difference would be 1. And you'd be left with the reciprocal of the film speed. So in this case, we divide by 1/60th of a second per frame, multiply by 2 frames, the frames cancel out, and we get seconds. So that's why you got to show all your work. Every step you should put the units in, because the units are going to tell you what to do. I'm a stickler for units. Let me give you an example. So this is probably about 20 years ago. So there was a flight to Mars. Some days humans are going to go to Mars. We got a ride on SpaceX recently, and that avoided us having to go to Kazakhstan and hitch a ride with the Russians, as we've been doing for the last decade. But eventually we're going to get to the point where we're going to have rockets that are going to be able to get us to Mars. And when we get to Mars, we're going to have about 7 months of microgravity or weightlessness, and then a few months, 5 to 7 months on Mars, where we're dealing with 1/3 of the Earth's gravity and then weightless conditions, again, unless we can figure out artificial gravity. But that usually involves rotation, which makes people kind of sick sometimes. So we still have a way to go with using centrifugal force to be able to generate a artificial gravity out in space. So what we've been doing instead is trying to exercise, and that's been helpful, but it's really hard to design equipment that gets the type of dynamic forces you see on Earth. Just running, for example, can produce 2 to 3 times the type of the person's weight during push-off and while people are landing. If you're playing volleyball, it can be 3 to 5 times, especially when you land. So, and when you're weightlifting, the forces on bones and muscles can be really large, hundreds, thousands of pounds. And that's really tough to try to replicate in a space environment. So we're working on it, we're getting better. We've got a couple of machines up now that are making some difference, but it just depends. Now, part of the problem is that in order to reduce the effects of spaceflight, the astronauts have to exercise 2.5 hours a day. So we're trying to figure out, can we cut it down to like 10 minutes or 30 minutes, get your aerobic in and then get your weightlifting in, maybe, 30 to 60 minutes, hopefully. So got a long way to go. But so back to this problem. So we have 2 frames elapsed, and that means when we divide this, it's going to be 1/30th of a second. I can put this in the denominator. So we've got 135 minus 110 degrees, and that's divided by, let's see if I can get in here. Here we go. Let me do it this way. 1/30th of a second, that's better. Excellent. Okay, so when we crunch that out, that's 750 degrees per second. Then I just took that to standard units by converting degrees into radians. That's 13.09 radians per second. So that's pretty amazing. You can see peak joint velocities in sports that can reach 2,000 degrees per second. Oh, the units. Sorry, I need to finish the story about Mars. Okay, so it's going to take about 7 months to get to Mars. The key is about 20 years ago, we sent a probe to Mars. And as you know, a number of these probes have gone to Mars. And when they land, there's actually a tetrahedron of balloons, if you will, that are inflated, that cushion the blow. And then it kind of turns over and a little dune buggy comes out. Well, this one time there was a small miscalculation, and it was a units problem. You might imagine to send spacecraft to Mars, you got thousands and thousands of calculations, and you've got to get all of them right, because physics doesn't care that you got 99.99% of the calculations right. It's that 0.1% that unfortunately might make the difference. And that was true here. So what happened was there was a units problem. I think it was actually a conversion problem. And because of that, when the Mars buggy is going to land, there's a parachute that goes off about 50 miles above the Martian surface. The atmosphere is thin, so it takes a long time for it to slow down. The good news is there isn't nearly as much gravity, 1/3 of what we see in the Earth. So, and it's a huge parachute. It was supposed to be released, the parachute, 50 miles above the Martian surface. It technically deployed 50 miles under the Martian surface. So that's your $2 billion mistake right there. Yeah, units count. They definitely matter, no question about it. So keep that in mind. We're going to do another calculation with arc length again, except I'm going to use this to calculate a curvilinear velocity. And so that will be the club head. Now we're looking at the club head moving around the wrist. So with a golf swing, you've got this kinematic chain where you have the trunk moving first, and then the shoulders rotate, and then finally this rotation around the quote-unquote wrist, where we have pronation and supination of the forearms and medial and lateral rotation of the shoulder. So let's say that we've filmed this with a real golfer. Let's say you go from 196 degrees to 268 degrees around the wrist. So we're looking at movement around the wrist. You can also calculate movement around the shoulder and movement around the torso. If you add them together, you're going to get club head speed, which for someone like Rory McIlroy is probably going to be close to 120 miles an hour. I think Brandon DeChambeau has hit over 130 miles an hour, which you usually don't see except for long driving contests. So now he can hit it close to 350 yards. So he can just hit wedges. That's kind of this is kind of a recalibration of golf courses that had been basically Tiger refitted. Tiger Woods used to be the longest driver. He no longer is. He's had back surgery, knee surgeries, all kinds of problems over the years. He can still play great golf and win some tournaments, even a major recently. But He's no longer the longest. So DeChambeau increases power. When he increased his power, that resulted in the ball going a lot farther. Okay, so we'll do this calculation around the wrist. This will be really the wrist, the movement of the club head around the wrist. If we added, again, wrist movement and torso movement, we would get the total club head speed. Here we're going to calculate a little over 100 miles an hour, I think. But if we looked at the total and added in wrist movement and then trunk movement, we'd probably get about 110 to 115 miles an hour, I think. So this was filmed with Scott Demery, who is our scratch golfer and ultramarathon runner, which we'll talk about some more. So 268 minus 196, we'll have to convert that obviously into radians, multiply. I'm going to assume that the club length is going to be the radius of the circle. It's a little bit of an assumption. So arc length is the radius times the arc. Velocity is distance divided by delta t. Here, this distance and this arc length are going to be the same. Arc length is a curvilinear distance. So arc length divided by time. So here we go. We've got a 72-degree arc. We're going to convert that to radians. That's 1.26 radians. We multiply by our ratio again. And then the arc length is the radius times the arc in radians. So that's 1.1 meters times 1.26 radians. That's 1.38 meters. Okay, so let's calculate velocity as the arc length. That's the curvilinear distance divided by delta t. This is these are consecutive frames, so the film speed was 1/30th of a second. So 1/30th of a second times 1 is 1/30th of a second. So it's 30 times 1.38, and I get about 41.5 meters per second. So this is close to 90 miles an hour. If we added in the wrist movement and the trunk movement, we probably would get probably close to 110, I would guess, which isn't bad for a scratch golfer. It's pretty good. Most people who are duffers just hit every once in a while, like myself. If they can hit 90 or 100 mile an hour club head speed, they're doing pretty good. If you can clear 100, get up to that 110 level or above, you might be able to hit it close to 300 yards. Okay, we're going to look at another application, and we're going to start using graphs a lot. You're going to be generating graphs in the laboratory. Here we're going to use a graph to tell us about velocity. How are we going to do that? This is a position time graph. So we're going to look at changes in position in the y-axis, changes in time in the x-axis. So remember, the slope of any line is the change in the y variable divided by the change in the x variable. So that means the change in position divided by time. By definition, that's velocity. If we were doing some calculus, we would differentiate basically dy divided by dx, or d position divided by dt, and that would give us the same thing at an instantaneous level. So this, not surprisingly, is what goes on in the middle of the 100-meter dash. This is where most people reach their peak speed. At the beginning, we have an acceleration phase where the slope of the line is increasing. So the slope of this line tells us about velocity. The steeper the slope, the faster the velocity. So it's a little intuitive, I think, I hope. And the flatter the line, the slower the velocity. So someone, maybe myself, running the 100-meter dash, I'm going to generate a curve or a line here. It's going to be considerably flatter. So B is Usain Bolt and A is me. There's no question Usain Bolt can generate a much faster velocity. Change in position divided by change in time. So position time graphs can tell us about velocity. They can also tell us about acceleration, because if the curve is going up, we're accelerating. If the curve is going down, we're decelerating, even though technically deceleration and acceleration are the same thing. We're changing our velocity, whether we're speeding up or slowing down. It really depends upon your reference system. So, okay. And again, this is the type of curve we'll see in that 100-meter dash. We got 3 phases. Phase 1 is the acceleration phase where the slope of that curve is increasing. In the middle, we have kind of a maintenance phase where we've reached a peak speed. It can be between like 40 to 60 meters out, depending upon the sprinter. Most people start to slow down about 70 meters out. And they do so because of the energy system that they have to use. So over the first few seconds, we're mostly using ATP. Then we use the phosphocreatine system. And when we break down phosphocreatine, it releases inorganic phosphate. And inorganic phosphate can interfere with actin and myosin cross-bridging, and that actually slows you down. So most people, the 100 and 200-meter race, at the end of the race, they're actually slowing down. The 200-meter race is probably a little bit of lactic acid as well. You really feel it, though, in the 400-meter race because you're generating huge amounts of sustained power for, depending upon how fast you are, from 3/4 of a minute, about 45 seconds, to almost a minute. You know, if you're a high schooler or junior high or someone like myself, might even take more than a minute today, probably would. But what you're going to feel over that last, 250 meters or so is a lot of lactic acid buildup. And remember, lactate, hydrogen ions, they actually interfere with your ability to be able to, A, produce glycolysis and therefore use and generate ATP, but also it interferes with the contractile apparatus, again, meaning actin and myosin cross-bridge forming. So that results in fatigue. Fatigue is just a way of really making sure that your body doesn't injure yourself more than it is already. So it is kind of a defense mechanism. Once the race is over, then you literally can walk it off or jog it off for about 20 minutes. What do I mean by that? By continuing to exercise, but at a lower intensity, actually clears lactate. The muscles will use lactate. Your heart uses lactate. Your brain uses lactate. Your brain loves lactate and glucose. That's what it lives on. It can live on ketone bodies. If you go on a keto diet, you'll probably lose muscle, bone, water, which comes from glycogen. And glycogen, you'll have a hard time losing fat. And your breath will smell bad. And there's potential to over time to become insulin resistant. In some cases, in people who are already obese or maybe pre-diabetic, it seems to help for a while. But we like to think about, because it's hard for people to sustain something like that. Keto diet isn't fun because your caloric deficit's 1,000, 15, usually 1,500 calories per day. You're on a very low calorie diet, high protein diet. Good news about high protein diet is humans, we've got about 2.5 times as much the kidney space as we need. And that's because our ancestors every once in a while would catch a lot of game and they'd have to eat it, or they would cook it and eat a lot of it, and then dry it out or salt it, pepper it up. That's actually how we preserve things. Sugar, alcohol, drying, spices, salting, what am I forgetting? Pickling. So those are the ways that people, before there were refrigerators, preserve things, because you couldn't keep the stuff around forever. So, that's why people use like dried fruit, not glucose, sucrose actually reduces, breakdown. What all of those things actually do, including refrigeration, is they reduce oxidation of oxidizing food. That's what causes food to break down and go bad. It starts to oxidize and then produces some nasty chemicals, including formaldehydes. We noticed with food breakdown, or people did, that sometimes you could use some of the products. Like that's how we learned to make vinegar, which we use for pickling and use for preserving. It actually came from food that was starting, I would say going bad, but starting to metabolize a bit past the usual ripeness, etc. Okay, so There's Usain Bolt yet again. So that leads us right into, speaking of Usain Bolt, locomotion. So locomotion is the ability of humans to be able to move their legs, move their center of gravity forward. So for us, walking and running are the two typical types of locomotion we see. A horse has kind of a walk or canter. It's got a trot, it's got a gallop, etc. My dog's got the same thing. It can kind of trot for a while, and then it can gallop. It's much faster than I am, even our big lab. But they're, especially on a day like today, which means most of the next 4 or 5 months around here in Texas is going to be summer for a long time. If we're not in shape, humans aren't so good at dissipating heat, even though our ancestors were. Dogs are even worse at doing that. So she likes to go running, but by the time it's over, she's definitely ready to sit on the tile and cool off for a long while. And I'm ready to get a cold drink. So for us, we mean walking and running. And there's some unique stuff about locomotion we'll talk about. Some adaptations that we mentioned before that are still incredibly important. Part of the reason why we're really good, we're actually relatively efficient bipeds. In fact, we're oftentimes more efficient at being a biped than many animals are at being a quadruped. Not all, but many of them, especially if we sustain it for a while. And so we can thank our gluteus maximus, gluteus medius, and minimus, the angle for the neck of the femur, our ability to be able to dissipate heat, our ability to be able to climb. That's not where that gluteus maximus, which is kind of maximus, comes in. So we're going to talk about some strategies related to endurance versus strategies related to power, sprinting when we really need it. So with locomotion, we're going to look at gaits and gait cycle, and that's the time and position from when a foot strikes the ground to when it strikes the ground again. So maybe the right foot hits the ground. You go through a complete cycle with either running or walking. The right foot hits the ground. Again, that's the completion of the gait cycle. Now we repeat gait cycles over and over again. So the number of gait cycles per second is something we call the stride rate. The distance covered for a gait cycle on average is called the stride length. So the rules are we can think about our feet being either in the stance phase. So this is Martha, her right foot's in the stance phase. She's pushed off. Now her foot's in the air. It's in the swing phase. So with running, only one foot is in the stance phase at any time. There's at the very beginning, the end, and the very middle of the gait cycle, both feet are actually in the swing phase. They're in the air. With walking, both feet are in the stance phase at the beginning, the end, and the middle of the gait cycle. Way back in the day, they used to actually cover in the Olympics race walking. They don't do it anymore. But they used to cover race walking. That was actually a big thing back in 1964, the Tokyo Olympics. So locomotion or gait velocity is actually a combination. It's actually the product of the stride length and the stride rate. And I'm going to show you why in just a minute. So again, with the gait cycle, you can have the stride length. That's the distance covered by one gait cycle. It's measured from heel strike to heel strike, or foot strike to foot strike. In the units are meters per stride or feet per stride. That makes sense. This is the distance divided by each stride. Stride rate is the number of gait cycles we take per minute or per second per unit of time. So it's strides per second. Those are standard units. If you multiply together the stride length and stride rate, let's say stride length in meters per stride, maybe 2 meters per stride, times 4 strides per second, that would be 2 times 4, or 6. 6 what? The strides cancel out, and we're left with meters per second. So it's velocity. Running or walking velocity, therefore, is the change, or is the product of the stride length and the stride rate. Stride length in meters per stride. times the stride rate in strides per second. So if we have a stride length of 2 meters per stride and a stride rate of 3 strides per second, that gives me 2 times 3. Strides cancel out. We're left with meters per second. That's 6 meters per second. If I reduce the stride length to 1 meters per stride, in order to achieve that velocity of 6 meters per second, I'd have to double that stride rate to 6 strides per second. So if one goes up, the other one has to go down if we maintain a certain velocity. This is going to be important because it's going to help us to understand strategies that the body uses for both endurance and reducing fatigue, as well as power and increasing our speed when we're sprinting. So we're going to introduce terms, reintroduce, since you guys have physics, terms like work and power and energy and efficiency, and define them and actually use them here. So this is a classic graph. It's a little bit more complicated than most because it's got 2 y-axes. But the reason we have 2 y-axes is that running velocity, which is on the x-axis here, is the product of, again, the stride length times the stride rate. Okay, so let's say we're walking at about 2 or 3 meters per second. When we start going to about 4 meters per second, most people are starting to jog. And this is kind of the endurance running aspect of it here, 4 to 5 meters per second. That's where most people are when they jump on a treadmill. So right in here, really good endurance runner might be about 6 meters per second. So this is on average. So in order to increase that running velocity, we've got to increase stride length or stride rate or both. Okay, there's no other choice. So notice that as we increase running velocity when we're jogging and running related to endurance. So this might be a pace, for example, that you can keep up for a couple miles. Or if you're in really good shape, like a 10K race, and you're really in good shape, maybe a marathon or half marathon. So notice what happens between like 3 to 5 meters per second. Are we increasing stride rate very much? No. Most of the increase in the running velocity is accomplished by increased stride length. So there must be a reason for that. Notice that this relationship doesn't continue. It changes as running velocity gets higher. So when we get to 8 meters per second above, you're sprinting. 8 to 10 to 12 meters per second, you're going fast. Notice between like 8 to 10 meters per second, what happens to stride length? Hardly changes at all. Mostly increases stride rate. So what's the difference here? Why? Why is there a difference in strategy? So we've got a high stride rate. That's going to be, linked to sprinting. And as we're going to see here shortly, power. High stride length, though, helps with efficiency. And we're going to define that in just a second. And that means endurance. Endurance just means the ability to maintain a certain power output and reduce fatigue. Not easy to do. Takes a bit of training. Trying to get back into it. Unfortunately, the weather's getting hot. And I guess I'm going to have to do more treadmill exercises as we move along. So we have to make measurements, okay? So whether it's biomechanics, and that can mean a lot of things. We might have to look at the energy that we're using. We might be looking at someone's gait. We might be measuring that. We might have a force or pressure played out. We might be measuring torque to see what's going on with our knee extensors and plantar flexors, etc. So the 2 ways is, we can measure metabolism, direct calorimetry or heat, or indirect calorimetry, oxygen consumption. So when you hook someone up, either with, that's a Douglas bag, believe it or not. This is at the U.S. Olympic Committee site in Colorado Springs. Here we see someone in, I guess, an exercise physiology setting. Here's more an athletic setting. They're hooked up. We're measuring oxygen consumption with an O2 and a CO2 cart, which is right in here. There's the metabolic cart. I don't see them here, but there would be something to measure how much airflow is going through the system and also the O2 and CO2 levels. Once you have that in the expired air, then you have a pretty good idea of what the oxygen consumption is of that individual. There's some rules though. You have to get a steady state measure, and that's going to mean at least 2 or 3 minutes, because it takes 2 or 3 minutes for most humans to reach a steady state. Dogs, horses, equine, excuse me. A lot of other species are quite a bit faster. Recently, it was discovered that women have a little faster kinetics than men. We're going to talk about that as we move on. The energy usage has to be 100% aerobic, and that's why it's going to take 2 or 3 minutes. You need a valid, reliable system of measure. It's actually not as easy to make really good VO2 measures as most people think. A lot of carts aren't calibrated too well. So a lot of things you have to consider: athletic performance. You're trying to improve quality of life. Maybe you're trying to increase aerobic capacity, and look at that. Maybe you're trying to increase the efficiency of gait. Sometimes you have people who've had strokes or orthopedic problems, joint, maybe a bone fracture, injury risk. So there's a lot of application here. We're going to really focus on locomotion and initially efficiency. So this is the Nobel Prize here. So there'll be a few instances in the class where we'll bring out a Nobel Prize winner or 2 or 3. When you see that, it's probably important. Not that everything we go over is not unimportant. Everything is. I wouldn't waste your time. But this is A.V. Hill, won the Nobel Prize with Dr. Meyerhoff in the 1920s. And they were focusing on the energy it takes for muscles to contract and skeletal muscle metabolism. They isolated muscles in a saline bath. They also looked at whole animals, mostly rodents, etc., and other animals, and measured oxygen consumption. This work was carried on by Dick Taylor, who we mentioned earlier, and a number of other people. He lived in England, and one of the things I didn't know about him was that there's an article recently published, a historical article, that went into a lot of detail about A.V. Hill during World War II, helping to rescue academic professors and scientists from Europe, especially from Germany. Many of them were Jews that he rescued. There were Catholics and other people who were running for their lives during World War II, away from the Nazis. And he helped to try to find homes for them in England, fight people who were trying to intern some of these individuals, and helped found places all over the world, including the United States, South America, Asia, etc., Canada, elsewhere in Europe, for them to go, and has served a very important purpose there. His Nobel Prize in skeletal muscle metabolism, one of the things that came from this research is the energy of shortening. So we know every time a muscle contracts, it has to overcome internal viscosity, and when it does, it takes a significant amount of energy. There's also the energy of metabolism involved, but it takes about 5 joules of energy per kilogram of mass per stride. So another way to think of it is 5 joules per kilograms times strides. It means the same thing. So it means that the more mass something has, the more energy it uses. That makes sense. The more strides a person or animal takes, the more energy it uses. It makes a good deal of sense as well. So the farther we walk, the more energy we use. That's good, because if we walk 2 or 3 miles a day or run 2 or 3 miles a day, it can make a difference in terms of our energy consumption during the day, and can help us with weight maintenance and weight loss. This also can help us, I think, to understand some of the strategies involved in the body when we're endurance running versus sprinting. So the notion is, if it takes 5 joules of energy per kilogram for each stride, if our stride rate could be lower, we'd use less energy. Aha. So that indeed is what it's about. So we're going to talk about gait efficiency. Very important for endurance runners, important for our ancestors. We work with groups, teams, to try to catch prey, etc. And even though there are people like Usain Bolt around, most people, in order to survive, sprinting didn't really help that much. What helped was the ability to be able to run for a significant distance. It could be half a mile, it could be a mile, it could be a few miles, to be able to hunt down some prey if we needed to, especially with teams. So that limited the amount of running that we had to do. But when we look at our ability to be able to dissipate heat, we also have a large surface area to mass ratio. We have these very fine hairs that sometimes you can hardly see that are on your skin. They help with heat dissipation as well. Our ability to redistribute blood flow to the skin and sweat, all of those things really help. Okay, so if we can make our running more efficient, that's going to help us or help our ancestors in hunting down prey and escaping. As hunter-gatherers, carrying back fruit, nuts, game, etc. All of that's incredibly important. Okay, so if the energy is shortening, is 5 joules per kilogram per stride. And the next thing we need to do is introduce some terms. So efficiency here is not a very general term. It often is when people talk about efficiency in advertisements on TV, but here it's really specific. This is technically gross mechanical efficiency. It's the mechanical work that you've done in joules, this is the metric system, divided by how much energy it takes to be able to produce that work. That's also in joules. Because they're in joules, we can express this as a percentage by multiplying this ratio by 100. So we're going to be doing that over the course of time. Then we need to talk about things like work, mechanical work, since that's efficiency is work done divided by energy. Work is basically the product of a force being generated and then how far we've either lifted or moved that object. That product of force and distance gives us work. Power is work rate, if you're wondering, so keep that in mind. We'll need to define force. Force is the ability to cause a change in motion or a change in the velocity vector. The angular equivalent of force is torque. That's the ability to produce angular rotation by increasing the angular velocity. Energy here will just be the energy used as the energy consumed by the body. Energy can also take all types of forms, so I shouldn't limit it to just the energy consumed by the body, because we're going to talk about along the way kinetic energy, the energy that can be stored in springs in our lower extremities, like the arch of our foot, the Achilles tendon, muscles in the lower extremities. Some of that can be converted to kinetic energy, which is the integral of momentum, if you're wondering, but it's basically 1/2 times mass times velocity squared. There we go. So as we're running, and let's say that we want to improve our mechanical efficiency. We want to improve our mechanical efficiency. We can do so by lowering the energy costs. So it means that, let's say we're running at a certain velocity or pace. If we can maximize our stride length, that means that the stride rate decreases. There's an inverse relationship between these two. When we were doing the math problem a little while ago, we saw this. So if we double stride length, stride rate is cut in half. The significance of that is that as I'm taking, let's say, instead of a greater number of strides, I'm taking fewer strides, that means there's less energy used in that exercise. So if I just flip these, can I flip these now? I'm going to flip these because I can. There we go. If I reduce the number of strides, that reduces the amount of energy that I use. Reduce the strides, reduce the energy that I used. Okay. So in order to reduce the strides, we have to reduce the stride rate. To do that, we have to have a large stride length. So we noticed a little while ago, and this is on average, you don't have to be a world-class athlete to be able to do this. We noticed that as people are going from walking to jogging, endurance running, that you don't see a significant increase in stride rate It's a stride length that goes up. Okay. So that's another clue that maximizing stride length is really super important. So that means it's not always the case, but often people who are good endurance runners have fairly long legs. It gets to be difficult when people get much larger and taller because they're often heavier and it's harder to move around. So optimally, you're looking at people usually that are between about 5'7", well, for a woman about 5'5", 5'5" to 5'7", to roughly about 5'10", 5'11". It just works out that way. With a kid with really short legs, they have to burn up a lot of energy when they're running, so you won't see a lot of good endurance runners that are younger than about 10 or 12 years of age. This also is true in the animal kingdom. So a rat or a mouse, they actually have a high aerobic capacity, but because they have teeny tiny legs, they have to take a lot of strides. Short stride length, that means high stride rate. They have to take lots of strides. That uses a lot of energy, and they're not very efficient runners. So that's an advantage for us. So again, reduce the number of strides. It reduces the amount of energy that you use. If you reduce the amount of energy, then mechanical efficiency goes up. So this is what science is about. It's all about a lot of if-then statements. If this happens, then there's some consequence. If stride length goes up, the consequence of stride rate goes down. If that is true, then since I know that there are 5 joules of energy per kilogram per stride, I know that as if I take fewer strides, there'll be less energy that my body has to use. And if I use less energy, then I become more efficient. So it's a step-by-step process. Works like engineering. That's why engineers are often the people that teach biomechanics classes, or people who've had a background in engineering. And really today, now that biology has gotten into it, it's kind of funny because the engineers are trying to catch up with the physiology and biology. And they're kind of dusting us right now in terms of tissue mechanics. So I really want to see kinesiology get into that area a lot, because that area is the future of sports medicine. That's where sports medicine's going. It's going into biologics. It's going into 3D bioprinting. It's going into hydrogels. It's going into learning about mechanisms that involve inflammatory signaling and oxidative stress and stress response proteins, and proteins like collagen and actin and myosin that make up the body of muscles and bones and tendons and ligaments. It's really that combination of biology and biochemistry and biomechanics at the tissue and cell level that's going to lead to how we can recover faster from a joint sprain. How can we replace cartilage that's been damaged or lost due to arthritis? How can we improve our ability to be able to resist against rotator cuff problems by introducing really targeted inflammatory drugs? How can we increase the healing capacity and reduce the healing time for tendons and ligaments that have been injured? So we talked a little bit about this at the beginning, where I think biomechanics is going. And it's going to be a critical part of I think, the future that you guys are going to get to see in the next 20, 30, 40, 50 years. It's going to be exciting indeed. Okay, so getting back to gait efficiency. Here's a creature with pretty good gait efficiency. You got to pretty much trick a horse to be able to catch them, because they can go 40 miles an hour for a long time. They do get hot eventually. So if you're on a horse, you have a better shot. It was difficult, I think, for ancestors initially to get horses, but they like sugar. They like some stuff we were trying to feed them, so we found some friendly horses and then raised them, etc. And then as we were able to get on horseback, we used lassos and ropes, etc. So eventually, it took a while with horses, but the horse was a game changer because it made people more mobile, so they could be involved in trade. Unfortunately, they were used for wars and conquering as well, and also to help to carry things, because these are 1,200-pound creatures. Okay, so if the energy of shortening is 5 joules per kilogram per stride, and we want to use less energy and increase our efficiency, we're going to maximize the stride length and decrease the stride rate. We saw that in just a moment ago in that graph, but you also see it in endurance runners. So here's the unfair thing about world-class endurance runners. They have a really high, this is VO2 max, so this is aerobic capacity, right? Aerobic capacity. And that's the ability of your cardiovascular system to pump blood, get oxygen to the tissues, for the tissues to take them up. Typical person who's healthy, college age, you guys look in pretty good shape. Aggies have a tradition of exercise. A lot of that has to do with the core, but some of it's just Texas A&M. Most of you probably are 45 mLs of O2 per kg per minute, maybe slightly above that. But typically, healthy college age persons, 40 to 42 mLs per kg per minute. With training, let's say you start off at 40, you might be able to increase it 20 to 25%. So 50 to 55 mLs of O2 per kg per minute. That's kind of the ceiling. It varies from individual to individual. Some people are more trainable than others. World-class endurance runners. How do you get there? Well, you got to pick your parents wisely, first of all. Second of all, you got to train like crazy. We did a VO2 max, this is way back in the day, of someone who had come back from Christmas vacation, and actually along the way, he had his money and clothes stolen, but didn't tell us for a while. And so we did a VO2 max test on him, and he hadn't eaten in 3 days. He didn't tell us that. And so afterwards, he collapsed and scared the heck out of us. But he was okay. He revived a minute later. That was probably the scariest thing I've ever seen. Then he revealed, oh, I haven't eaten in 3 days. I'm like, kidding me. But in that shape, he was 60 mLs of O2 per kilogram per minute. He hadn't been training. After he trained, I think he probably got up to about 70 mLs per kg per minute and ran some races, but just crazy VO2 max. Here's someone hasn't eaten, hasn't trained. I mean, really unbelievable. So these world-class athletes, we sometimes see, and they have really high VO2 maxes, these endurance athletes, and really high lactate thresholds as well. You can see 70, 75, 80, even 85. That's a typical range. So I've rounded off to 80. That's a little on the high side, but I think Lance Armstrong back in the day, and when actually wasn't blood doping, was about 78 mLs of O2 per kilogram per minute. And that was pretty steady for the most part. University of Texas people, those TU people, tested them. And I think what they mostly saw with training was a higher lactate threshold. So we could just maintain that high work rate without building up a lot of lactic acid and getting tired and fatigued, and et cetera. 90 is kind of mythical. There have been allegedly some people who've reached 90 or above. I'm like, it's pretty amazing. A guy named John Shire used to play basketball for Duke, allegedly hit 90, but they don't have a strong exercise physiology group there. So I've been always skeptical about that number. The highest I've ever seen or tested was about 83 mLs per kg per minute. It was someone who finished 10th in the Ironman triathlon. That's where you go out and like swim for 10 miles, you run a marathon, then bike for 100 miles in Hawaii. Crazy. Mike Kirtley was the guy's name. And I'll tell you a story. He was in a physiology laboratory with us. And this was kind of an advanced course we were taking over in biology. And we had fun with the TAs. So the TAs wanted someone to run up a set of stairs and run down and then check their heart rate before and after. So we got him to say, just think about getting nervous a little bit. So when he did that, see, his resting heart rate is usually about 45. So we got him up to 50. And then he was in such great shape, he ran up and down the set of stairs. And when you're in that kind of shape, your vagal tone is really strong. So he ran up and down, and his heart rate didn't change at all. It was like 48. I think it was lower. It was about 48 to 50 before he went up the stairs. It was like 45 after he sat down and rested. And we had a lot of fun with the TAs because like, oh, that's broken. Your equipment's broken. And we had him do it again. And his heart rate was still in the 40s. So we had fun with that. Anyway, his VO2 max was about 82, 83. We got really close. I thought close to breaking our personal, the labs record. This really belongs to people. But there was a world-class cyclist, and we were on the cycle ergometer, and we got to the last stage. The next to last stage, I think he was close to 85. You know, it was unofficial until you actually get there. So we thought we were going to clear 85 or above. It was like, ooh, we were in this almost mythical range. And about 20 seconds left. And, you know, we're yelling, finish, finish, go, 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 go. There's a lot of yelling with the VO2 max test near the end. All of a sudden, he just stopped. And, you know, you had the mouthpiece and you had the nose clip. And it gets a little claustrophobic in there. He just freaked out. He threw the mouthpiece down and the nose piece, walked out. We never saw him again. We tried to call him. He wouldn't come back. So he had a meltdown and left, and couldn't get him back to do that super VO2 max test again. Okay, here's something depressing. A rat, fat old rat at rest, doing nothing, maybe eating some garbage. 95 mLs of O2 per kilogram per minute. A trained one can get up to about 100 mLs of O2 per kilogram per minute or above. Now here's the good news. If we ran a mile race, by the way, think about a race where you're running at maximal aerobic capacity or VO2 max. Is it 100 meters? Nah, you're not even using glycolysis then. Is it 200 meters? No. Is it 400, 800? Nah, not really. Because it takes 2 or 3 minutes just to get up to VO2 max. It's the mile. So a mile or 1,600 meters, that's where you're really exercising at VO2 max. If it's above that, like 5 or 10K, especially the marathon, you're running closer to your lactate threshold because you can maintain right below, right at that lactate threshold for a fairly long period of time without getting too much acidosis and lactate levels built up. Okay, so the good news is that even though this rat is a super high VO2 max, even if you're here instead of at the world-class level, which again, they pick their parents wisely, you're going to beat the rat in that mile race. You're going to beat it easily. You're going to crush it. And that's because the rat has teeny tiny legs, so the stride length is low. And because there's an inverse relationship, that's the key thing. That means that stride rate is high. And if the stride rate is high, well, guess what? That means that we take more strides, use more energy. Energy's in the denominator here, so that means efficiency goes way down. And that rat's in big trouble, and we're going to win. So there's the good news there. A thoroughbred horse kind of has it all, has that high stride length, has a super high VO2 max. They're relatively efficient runners, and so that's why Secretariat, other thoroughbred horses can run a mile in about 2 minutes. The fastest human can run a little under 4 minutes for the mile. So they're dusting us. They have a VO2 max of 160 mLs of O2 per kg per minute. Secretariat evidently had a heart that was twice the average size for a thoroughbred. So we could have been talking about 300 mLs of O2 per kilogram per minute. And that's why when the trainer pumped up the training before the Belmont Stakes, which everybody thought was going to be a mistake, that the horse was able to take off, run really fast at the beginning, and just maintain that rate because it can maintain with a long stride length and a high VO2 max. It could maintain that velocity throughout the entire race and won by 35, 40 lengths. So if you get to see either the movie or a clip, go check it out for sure. Okay, so when we're measuring energy consumption and looking at gait efficiency, we actually have learned a lot, not only from people over the years, but expanding on A.V. Hill. A.V. Hill, again, is this Nobel Prize winner from won the Nobel Prize in the 1920s. And the work he did led to gait analysis. Dick Taylor from Harvard measured gait analysis in all kinds of animals. They measured everything from ducks to lions. That's a llama. That's him with a llama. Way back in probably the 1970s, there's a llama with his mask on. So not just humans have to wear the mask. So the llama, fortunately, didn't throw the mask down and walk out. It stayed. We've worked with ponies back in the day. It takes a while to train them. Well, once you train them, though, they do pretty well, believe it or not. And they kind of tolerate it. And so they measured the efficiency and oxygen consumption of locomotion in all kinds of creatures. And humans do pretty well. In fact, we're actually just a little bit off the curve as bipeds, which is really unusual. So when we get to training, if we're training for something like the mile, which remember is run at VO2 max, you want to train to increase VO2 max, right? If you're training for the marathon or 10K race, they're run near the lactate threshold. So the training you want to do is going to be more conducive to increasing that lactate threshold. So that's going to be more long, slow training. The mile is going to be different though. When you're trying to increase VO2 max, running 10 miles is not going to do it. So my son had a coach when he was in high school. Matt, my son, ran the mile, sometimes 2 miles, but mostly the mile race. And the coach just had all the endurance athletes train the same. Didn't matter what they were running. They would get up and run like, I don't know, 8 miles at 6:30 a.m. and then 8 miles again at 5 o'clock p.m. Did that help much for the miler? Maybe a little bit, but if they were out of shape to begin with, probably, but not much because it didn't really increase their VO2 max as much as running their lactate threshold. Well, in the mile, you're running way past your lactate threshold, especially at the beginning and the end of the race. And even in the middle of the race, you're running at that VO2 max. So the way to increase VO2 max is to do interval training. And those involve like 400-meter sprints, then jog another 400 meters, sprint at 400 meters. They really hurt. No one likes to start off doing the interval training. After a couple of weeks, it gets better, but boy, those first couple of weeks of interval training, they're really hard. Or you can run up and down hills. That's a good way also to do some training for the mile. So it's a higher intensity exercise, and you can't train for the mile the same way you train for a marathon or half marathon or even a 10K. Okay. So with that in mind, high aerobic capacity really helps. Good stride length, high efficiency, good endurance, a high percentage of slow twitch fibers, that also helps. And that's largely genetic. You can shift about 10% with endurance training from fast twitch to slow twitch, but that's about it. And there's no training that can turn slow twitch into fast twitch. So for sprinters really pick their parents wisely because they have a high percentage of fast twitch fibers. They'll have a lot of muscle mass. Their anatomy is ideal in terms of producing very fast movements, but you're probably not going to see them running a couple miles. So in football practice, running 2 miles, that's maybe punishment, but that's not going to help anybody. Okay, so the transition from like walking to running, when we do that, it lowers our energy costs, believe it or not, and allows us, especially with a large gluteus maximus, springs in the lower extremities. The lower extremities can also act like a pendulum. These are energy-saving devices. We've got a big advantage over this creature in terms of being a biped. So this, of course, is a chimpanzee. Chimpanzees do locomotion on all fours. They can stand for a little while, but it's not for very long. They have flat feet. They don't have an arch in their foot. The humans do. That makes a big difference in terms of support and in terms of energy storage. Our Achilles tendon can store a lot of energy. We have a nice long one. These guys don't have a nice long one. Those muscles in the lower extremities can stretch and store spring energy. Our legs can swing and act like a pendulum. That's another energy saving device, especially when walking. So this is These are some, I think, 400-meter runners, and even that gait looks very efficient. One of the things I'm liking, what I'm seeing here is that notice that knee is not fully extended. You don't want to be fully extended when you land, either when you sprint or whether you're running an endurance race. They're going to land either on the toes or the arch of the foot. That's going to allow the arch of the foot, the Achilles tendon, the gastrocnemius, the quadriceps, and even the gluteus maximus and hamstrings to be able to store a significant amount of energy. It also allows, if the knees flex, we don't want to say bent in our class. Biomechanics, this is bent. Bending is a change in the mechanical shape of a tissue by causing tension on one side and compression on the other side. If someone's knee is bent, get them to a hospital right away. They rotate, they flex, they extend. You also have some rotation in the transverse plane. So that runner is going to land on the arch of the foot. That's what we're looking for. That helps us to be able to store energy. We've got these built-in oscillators. So these are kind of simple machines again that we can use to save energy that we use by taking strain energy and potential energy. Actually, strain energy or spring energy is another type of potential energy. Taking potential energy and converting that into kinetic energy. So this is the force that's stored in the spring. This is the energy that can be stored in the spring, like the Achilles tendon, the arch of the foot, includes the plantar fascia, the calcaneal, navicular ligament, the muscles in the lower extremities. They store energy and return that as kinetic energy. So kinetic energy is the integral. Let's see, I'm going to have to move this around a little bit or change my font size. Let me change my font size a little bit. There we go. I think I can make it. No, I'm not going to make it. Here we go. Boom. I'll make that a different color. There we go. Okay. So we're going to take some of this potential energy, spring energy that we're storing in the arch of the foot, the Achilles tendon, muscles in the lower extremities. We're going to convert some of that with a push-off into kinetic energy. So it's a way of saving the energy that your body has to use to propel yourself forward. Another way we can do this is when we run, especially when we walk, is our legs can swing like a pendulum. And then when we land, it acts like a reverse pendulum. Pendulums are energy-saving devices because they take potential energy, and that's the energy that you usually associate with an object like dropping from a certain height. So potential energy, kinetic energy. Potential energy, kinetic energy. I'm adding energy into the system, becoming potential energy, kinetic energy. So for a pendulum, as your leg is swinging, it's the mass times acceleration due to gravity times the height. As you start running, it gets interesting. You actually shorten the pendulum, and that shortens the frequency. So here's the frequency for a pendulum, and here's the time over which it takes. But pendulums are another way of taking potential energy and converting that also into some kinetic energy, giving you energy savings. So when people are running and walking, pendulum motion is probably a bit more energy saving for walking than it is for running. The spring forces, spring potential, stores and saves a bit more energy than the pendulum does for running. But nonetheless, during walking and running, both springs and pendulum save energy. So even though that we're a biped, we can store and save a lot of energy. And that means our efficiency, especially when we're in shape and young, of locomotion with walking and running is going to be pretty high because that energy that we're using is going to be low. So notice in these equations, like for the frequency, this is the oscillation frequency. Oscillators are things that go back and forth. So when you stretch a spring, it goes back and forth at a certain frequency. Pendulums go back and forth at a certain frequency based on the length. L stands for length here. The longer the pendulum is, the slower the frequency. The shorter the pendulum is, the faster the frequency. When you're running, you actually shorten that pendulum and allows it to go faster when you're sprinting. When you're walking, it's going to go slower, which is really pretty cool. Notice that pi shows up here. So it's not just for circles anymore. It's for oscillations, for all kinds of things. We see it in electronic circuits as well. So it's there in both sets of equations. Right now, we're just thinking about springs and pendulums as being energy-saving devices. And these equations help us to understand how that occurs. So understanding that both spring energy and the energy that can be stored in a pendulum are potential energy that can be converted to kinetic energy that can save us significant amount of energy when we're running and walking. So pretty exciting. Okay, so gonna go by, this is one of Dick Taylor's studies at Harvard. He was the guy I showed you, he was doing VO2 on a llama. He looked at all kinds of animals, lions, tigers, bears, everything. Our advantage are a lot of these adaptations that we've had over the last 1,000,000 to 2,000,000 years or so. Heat dissipation, the arch of the foot, the alteration at the hip joint. We've got that gluteus medius and gluteus minimus there with abduction. That's important because when our foot's on the ground in the stance phase, the only thing between us and the ground is the gluteus medius and the gluteus minimus. Then we have our large gluteus maximus, big hip extensor muscle. Helps us with running, helps us with climbing. That's why our gluteus maximus is big. When we look back at, and I didn't mean to do comparative anatomy, but if you look at, not that you wanted to look at the behind of a chimpanzee, they have a small gluteus maximus, small butt. Sprinters are going to have actually a fairly large gluteus maximus because they're using it to push off. Runners, football players, you probably notice that, shot putters, anybody where you've got a lot of hip extension. And this is true for runners as well. You got to have that. And that's going to help to propel yourself forward, reduce the energy that you use. And so here's B, that's us. That 55 to 60 degree angle. So when your foot is planted and you take a step, the neck of that femur is almost in a vertical position. And our friend, the chimpanzee, is a much flatter angle, probably 25, maybe 30 degrees. So here's Scott Demery, this ultra marathon runner we've talked about and golfer. And here when he lands, the ankle is right underneath the knee joint. That's exactly what you want. The muscles in the quadriceps and the gastrocnemius, those muscles have already turned on. They're activated. They're storing force and energy that can be used to propel himself forward. Here's the Badwater Ultra Marathon. This is kind of the ultimate marathon race. These ultra marathons are 24 to 48 hours. They're incredibly long. They use lots and lots of energy. So we want to talk about some cool things related to this. And obviously heat dissipation. Boy, this is extreme because they're starting in the middle of July. It's about 115, 120 degrees. They start at Death Valley and they wander around and climb up the Sierra Nevada, eventually halfway up Mount Whitney. It's a tough race, toughest endurance race we know of. Second toughest is there's one around Pikes Peak. Scott Demery's participated in that one, believe it or not, helped one of his buddies because you've got about 5 feet of width, maybe on the trail, 5,000 foot drop off on one side. It's a scary thing. And they run for 24 hours. So you need someone there. So this gets to a really interesting topic in terms of endurance running and endurance athletes. Once upon a time, and from my lifestyle, my lifetime standpoint, it's not a long time from yours. It is, it's way before you were born. But 1984, that's really, to me, not that long ago. The 1980s is, we had actually color pictures in the 1980s when you looked at athletes. In 1984 Olympic Games, that was actually the first marathon that was allowed for women, because they were worried, oh, the women might have trouble, etc. So something about westernized modern society. Maybe it's because of all the wars we've had. One of the things we've learned is that in terms of like pilots and in warfare today, that women do really well. Women are great pilots, by the way. But this is something we've learned in 1984, roughly, what's that, 35 years or so. So in the last 3 decades plus, we've learned a lot about women, their ability to be able to, and in the animal kingdom, we should have learned because the evidence has been there for a long time. There's the story about Hannibal and the female elephants he used to get over the Alps because the males couldn't make it. So we're going to talk about ultra marathons in women. Why are we going to do that? Well, I was looking at some world records, and this is a while ago, and I was thinking about the difference, because usually there's a little bit of a weight difference in men and women. And I first did a log scale for distance and time and looked at the world records for men and women with 100-meter dash, 200, 400-meter dash, 800, the mile race, all the way to the marathon. And when you do the log scale, it comes out pretty funky. But you notice, there's a change at the mile, and then it becomes kind of tougher for us, but we still do pretty good. The fact this is linear all the way up to the mile is actually pretty amazing. And then even after that, you go to the 10K and then the marathon, it stays on that line. It's pretty amazing. And when I calculated the difference as a percentage, it's about 10% difference as we go on a log scale, all the way from the 100 meters to the 26.2 miles that are in the marathon. So I was like, well, what happens in the ultra marathon? We know now that women can run the marathon. They do it just fine. They finish a little bit behind the men, but it's not much. It is not much at all. And most of the time, a female athlete who's running the marathon is going to beat almost all the males. It's only a few elite males that are going to be able to hang with her or beat her. But what happens in the ultra marathon? Are women going to have more problems? Are they going to have problems due to bone structure? Maybe there are differences in muscle metabolism and physiology. So over the past 3 decades, we've seen actually a fair number of women start to compete in these ultra marathon races. Brenda Guajardo, Claire Hyde, and a number of other winners of these ultra marathons. Oftentimes, they don't split the men and women. They start them all at the same time, and they finish at the same time. So do women have the right stuff to be able to compete in the Badwater ultra marathon and other ultra marathons? Scott Demery, the guy I've talked about, actually won one of these in Dallas. And so in Dallas, you didn't have mountains to climb or desert to work through, or he ran the Pikes Peak, so you don't have Pikes Peak to work with and major altitude. But he did have to run around a track for 48 hours. I think I'd rather do this. Give me the heat, give me the altitude, just don't make me run around a track for 2 days. But he won that race, and he actually did pretty well in the Pikes Peak race. And he was in his 40s. So this is one of the things to think about, is our ability, if we can stay in shape, to run and do endurance type exercise, can be sustained for decades. That's actually pretty exciting if you think about it. And we know anecdotally from athletes who continue to exercise, from farmers, etc., that they can maintain a lot of strength and endurance into their 60s and beyond. So it's never too late. Okay, so how are these women doing? They seem to be winning medals, especially during harsh conditions. The worse the weather is, the better the women do. In fact, there was a Badwater ultra marathon a couple of years ago. It was about 3 years ago now. And the men just started dropping like flies. It was really bad weather. It was terrible heat and lots of rain. It was actually got cold. You know, when you're up in the mountains and cold rain is on you, then that's, yeah. So the men were dropping. And so science has been looking at this and said, what the heck is going on? This, by the way, this is Maria Loreno Ramirez. She won the Puebla Ultra Marathon race. Again, men were competing. She did this in native gear. That's her native gear. Women have won the Badwater Ultra Marathon at least 3 times. Like I said, a couple of years ago, the men were just dropping like flies. So what's going on? Well, recently it's been discovered the past 3 years that women have faster O2 kinetics. They can actually use oxygen at the tissue level more effectively than men can. Also, there's a thought that fat metabolism, some of this is due to estrogen, some of it is other things. And maybe the pelvis can just take that, their pelvis is a little wider, can take that pounding maybe a little bit better than men can. So it's really interesting. The other thing to remember is that your mitochondrial DNA, they're passed down, not from your dad doesn't give you any, from your mom. This is why I have Secretariat here, because Miss Tweedy, I'm trying to remember Miss Tweedy's first name, I blanked out on it, but the owner of Secretariat, she looked at the mom as well as the dad when picking a horse, picking Secretariat. And that's actually true. Secretariat had lots of sires. None of them were any good. I think had some grandsons or great-grandsons who did, a couple of them did pretty well. So when breeding, she didn't breed Secretariat because she sold Secretariat as a syndicate, like a group. And so the group decided who was going to do what, et cetera. So that's the problem. You got to look at the mom. If you want to be a good marathon runner, maybe look at the dad. Mom, look at the mom. So that mitochondrial DNA is passed from mother to son or daughter, et cetera. So do women have the right stuff? It turns out, yes. When conditions get really hard, when Mother Nature, when conditions really knock it down, then who's the toughest gender? I hate, or sex, I hate to tell you, it's the females. So just remember that, guys. We should know that because I have a word for you if you haven't figured out. Childbirth, they're tougher. So conditions get bad, who's going to survive? It's not. And plus, we should know, especially in America, there's actually a fairly substantial difference in longevity between men and women. So, I mean, the clues are already out there. So there we are with ultra marathons. Oops. Here we go. Under harsh conditions, we want to make sure we get lots of hydration. Because our time is actually running a bit long, I think what I'm going to do is stop right here. So this is our first installment of Applied Kinematics. When we get back, we're going to talk about D.B. Dill. His name rhymes with A.V. Hill. D.B. Dill. D.B. Dill helped to found the Harvard Fatigue Lab. He's a pioneer of fluid replacement drinks. We're going to talk even about Robert Cade and Gatorade and even how that works. And then talk about sprinters who, like I said, are kind of, they pick their parents wisely. In humans, they're really kind of freaks of nature. We're built for the most part to be good endurance runners and also carry things. We're good at carrying stuff around while actually expending a lot less energy than normally one would think. That's it for today. I'm going to leave you with this beautiful picture of Lake Mead in Nevada. This is the Hoover Dam, and it's about 30 miles from Las Vegas, something like that. I've driven down there. It's pretty cool. So we're going to talk about the story about building the Hoover, used to be called the Boulder Dam, some of the problems they have there, and how that really revolutionized fluid replacement drinks. Okay, so have a great one. We will see you next time.